let's say you're standing on a beach. In case you need a diagram, this is you, and this is the beach. So you're standing on the beach, you're relaxing, you're enjoying your time after finals, and on the beach, there are some pebbles. In fact, they're the most perfect pebbles you've ever seen. And there's not just one, there's a bunch of them. And you're standing there and you're trying to think of what you can do with these pebbles. And maybe you think of trying to skip them on the water, but skipping pebbles is lame, and you're not lame, so you're not going to do them. Instead, you're going to play the Pebble game. Now, as a reminder, the Pebble game is a game played on directed acyclic graphs, where the idea is that you have a single sync vertex, which is your goal that you're trying to get to. But in order to place a pebble on any node, you first need to get pebbles on the nodes pointing directly to it, and only if there are pebbles on both the nodes pointing directly to it can you place a pebble on this node. Now that means you can place a pebble on any source vertex at any time, and the only additional rule is you're allowed to remove pebbles at any time. So in order to win the Pebble game with 3 pebbles on this graph, I could do something like this. And now that I've placed a pebble on the sync vertex, I've won the Pebble game. And what we showed in class was that if we have any constant in degree graph, then if the graph has v vertices, we have a strategy to pebble it using v over log v pebbles. And as you're standing there on the beach, you're thinking, can we improve on this strategy? Can we do better? And the answer is no. No, we cannot. And now for the rest of this video, we are going to be constructing some graphs. We're going to be constructing graphs that are hard to pebble. In order to do so, we'll start by making building blocks that we call super concentrators, and then we'll use them to build our family of super duper concentrators, which are graphs that will show that it takes v over log v pebbles to win the Pebble game on. So let's begin. What is a super concentrator? A super concentrator is a directed acyclic graph. So all of these edges are directed in this direction, such that we have some subset of entry nodes and some subset of exit nodes. And we have this very special property where for any subset of the entry nodes, so if I pick this one and this one and this one, and any subset of the same size of the exit nodes, then I can find paths connecting each of the entry nodes to an exit node and connecting each of the exit nodes as well, with the property that each of these paths is disjoint, that none of them share any edges and none of them share any vertices. And this is pretty cool because you can do this for any subset of these entry nodes and any subset of these exit nodes for this graph. And this seems intuitively very useful for the Pebble game, because if we have lots of disjoint paths from one end to the other, it sort of seems like it would require a lot of pebbles to get from one end to the other. But we can't directly play the Pebble game on a graph that looks something like this, because this isn't a constant in degree graph. Our theorem is only relevant for constant in degree graphs. So we'll try to build a linear superconcentrator, and we'll do so recursively. So we start with S1, which is just a boring sort of one entry node, one exit node, one edge connecting the two sort of graph. And then we will recursively build these graphs Sn, where Sn has n entry nodes and n exit nodes, and it has one like horizontal edge connecting each entry node to some exit node, and it also connects each entry node to this shrinking sort of portion of the graph called M, and then uses a smaller version of these Sn. So it uses S4M, where n equals 6m, so a 2/3 size graph, and then it re-expands the graph using the reverse of our shrinking graph M. Now, let's show that Sn is still a superconcentrator, and to do so, we'll look a bit at the structure of M. So M is a bipartite graph. It has 6m entry nodes and 4m exit nodes. And moreover, each of the 6m entry nodes has 6 edges leaving the nodes, and each of the exit nodes has 9 edges entering the nodes. And this is no matter what m or n is. Now, the thing we don't know is which edges are connected to which. And actually constructing this graph M is quite hard. You can read more about it in the paper. But we are going to just assume that such a graph exists with the special property that it's almost a superconcentrator. And what I mean by that is for any subset of less than 3m of the input nodes, we can find a subset of the same size of the output nodes such that we have these disjoint paths. And I'm not saying the superconcentrator property, which is that it's true for any subset of the output nodes, just for that each subset of the input nodes, there is at least one corresponding subset of the output nodes where we can do this. And what that means is that we can recursively show that each of our Sn is a superconcentrator. The way we do this is the following. Clearly, S1 is a superconcentrator, so that gives us our base case. And then for any subset of the nodes of Sn, so if we pick 4 of the input nodes here, and then 4 of the output nodes here, for example, then first what we can see is that if we pick more than half the nodes, then by the pigeonhole principle, at least all but half the nodes we can connect just by using these like across edges. And then what we have remaining is some k, where k is less than or equal to 3m nodes that we have to connect down to our shrinking graph m. But since we have less than half the nodes, we know we can use our special property of m to get some disjoint paths to the outputs. And we can do the same thing on the other end, where we can use the special property of m reverse to get disjoint paths to our inputs. And then we just need disjoint paths across S4M. But by our inductive hypothesis, S4M is a superconcentrator, so we can find these disjoint paths and we're done. So now that we have these linear superconcentrators Sn, let's look at some of the properties of them. First, we can see that the in degree of each of them is at most 9, and this is pretty easily proved by induction based on the fact that the in degree of m here is at most 9, and we can find that the number of edges in this graph is at most 45n, and this again is an inductive proof following from the fact that there are exactly 6n edges here. And what's cool about the number of edges being at most 45n is that this also tells us that the number of vertices in this graph, which is obviously at most twice the number of edges, is also going to be some constant times n. And this is helpful for us because if we want to prove stuff about the Pebble game related to this graph, we need to know the number of vertices to know approximately what v over log v is. So now that we have these superconcentrators, we can start building our super duper concentrators. And we'll look first at just what a super duper concentrator looks like, and then we can look at how we would go about proving our Pebble game lower bounds on these super duper concentrators. We again build these recursively. So we start with G8, and G8 is just going to be one of our super concentrators. It's going to be S256 because 256 is 2 to the 8th. And then what we do is for every graph larger than that, so for every Gn plus 1, we build it out of Gn. What we do is we have 2 to the n plus 1 input and exit nodes where we're divided into sets of 2 to the n. Then we connect them to a super concentrator of size 2 to the n, connect that to our previous super duper concentrator, so Gn, and then do the same thing but in the reverse direction. So we have another super concentrator Gn, we have super duper concentrator Gn, we have another super concentrator S2 to the n, and then we connect them to 2 sets of exit nodes. What can we say about these super duper concentrators? First, we can see that each super duper concentrator still has constant in degree. This again is something you can prove inductively following from the fact that our super concentrators have constant in degree. We can also prove inductively that for any graph Gn, the number of vertices is some constant times n times 2 to the n. And we have that a bunch of the subgraphs of these super duper concentrators are actually super concentrators. This is like fun to think about, so I encourage you to pause and think about it for a bit, like why this is true. But we know that like starting off, we have these building blocks, which are super concentrators, but also like this is a super concentrator, and this is a super concentrator, this is a super concentrator, and so on. There's a lot of super concentrators just in the building blocks of Gn plus 1. So what are we trying to show with the Pebble game? How do we go about this? First, we want to show that it requires theta of v over log v pebbles to win the Pebble game. And since v is c1 times n times 2 to the n, we can see that theta of v over log v means we want some constant times 2 to the n pebbles to win the Pebble game. And we're actually going to show that it requires that many pebbles to win the Pebble game on some set A. Where by win the Pebble game on some set A, I just mean that we want to pebble all of the nodes in A in any order, and they don't need to be pebbled all at once, just as long as we do them like one at a time is okay, or a couple at a time. And that's also pretty fun to think about if you want to pause and think about why saying that it's hard to pebble A also means that it's hard to pebble one singular sync node in Gn plus 1. Now, in order to prove this, we're going to use a lemma on super concentrators, which is essentially going to formalize the idea that we're talking about, that if we have a lot of node disjoint paths, then we need a lot of pebbles to get from one end to the other. Specifically, if we have j pebbles on our super concentrator, we have some set of at least j plus 1 sinks, then we can find n minus j entry nodes so that each entry node has at least one path to one of our special sinks that doesn't have any pebbles on it. Now, why is this true? Well, imagine we're trying to find a set of nodes that don't have this property. Well, if we pick any set of j plus 1 entry nodes, so let's say we pick these 4 entry nodes, and then by the definition of super concentrators, we have node disjoint paths to our sinks. So we have this, and then this, and then this, and then this. So we have these node disjoint paths to our sinks, and what we can show is that since there's j plus 1 paths, but only j pebbles, at least one of these paths must be pebble free. So the largest set we can get where none of the paths are pebble free must be of size j. So if there's less than or equal to j entry nodes with no pebble free paths, there must be at least n minus j entry nodes with pebble free paths. Now, using this, we're going to prove our big theorem. The big theorem is kind of long and complicated, which I'm sorry about, but it's basically because what we want to prove is that for each graph Gn, to pebble the graph, there must be some point where we have alpha n pebbles. And alpha n is just going to be 2 to the negative 8 times 2 to the n. So it's just some constant times 2 to the n. But in order to show that via induction, we need some stronger assumptions in our inductive assumption. So we add some conditions to our inductive hypothesis. So what we're going to say is that if we have any strategy in which we're trying to pebble 14 alpha n exit nodes, and in our strategy, we'll give some leeway. We can start with some pebbles on the graph, as long as it's not more than 3 alpha n pebbles on the graph. Then we can find some time interval, so not just a time stamp, but like some time interval within the graph, where during the time interval, we pebble at least 34 alpha n entry nodes, and for the entire time interval, there are alpha n pebbles on the graph. So let's prove the base case of this. The base case says for every strategy that we pebble 14 exit vertices of G8, and we can start with at most 3 pebbles on the graph, there's a time interval where there's just like a pebble on the graph for the entire interval, and we pebble at least 34 entry vertices. So why is this true? Well, we know G8 is just a super concentrator. It's just S256. And since we want to pebble at least 14 of the exit nodes, and we start with at least 3 pebbles at most 3 pebbles on the graph, we can apply our lemma, and we can just pick any 4 of these 14 exit nodes, and we can apply our lemma to these to say that there are 256 minus 3, or 253 entry nodes with pebble-free paths to these 4 exit nodes. And by the pigeonhole principle, that means there's at least one of these sync nodes that we pick which has 253 over 4, or 63 entry nodes with pebble-free paths to that exit node. Now that means that for any strategy, there must be some time interval where we start pebbling these 63 entry nodes and we end with pebbling this one sink node. And we know that we can find the time interval such that there's always at least one pebble on the graph, because if we take all our pebbles off the graph, then we've essentially reset the state, and we need to go back and repebble these 63 entry nodes to get to the sink node. So we have found a time interval where there's more than 34 entry nodes being pebbled, and there's always at least a pebble on the graph. So we've proven our base case. Now let's move on to our inductive case. Our inductive case is slightly more complicated. Basically, we will look at every strategy to pebble 14 alpha n plus 1 exit nodes of gn plus 1. And either the strategy falls into one of three special cases, or because it's not in any of these special cases, we now know more things about the structure of the strategy, and we can use that to prove the inductive hypothesis. So first, let's look at our special cases. So case one is we have a strategy where there's some time interval where for the entire time interval, there are 3 alpha n pebbles on the graph. And during that time interval, we pebble 7 alpha n of these nodes. Now, what does that tell us? Well, we want to apply our lemma somehow to get to some statement about the entry nodes. In order to do that, we need to know a maximum for how many pebbles we start with. We can do that by just extending this interval backwards. So let t0 be the first time before t1 at which there are at most 6 alpha n pebbles on the graph. So if at t1 there are at most 6 alpha n pebbles on the graph, then we're good and we don't need to do anything. Otherwise, we sort of rewind each step where we added pebbles before t1 until we get to a point where there's at most 6 alpha n pebbles on the graph. And then clearly, we're still in an interval where the entire time there's 3 alpha n pebbles on the graph, and this covers our condition of there being alpha n plus 1 pebbles for the entire interval. Then we can apply our lemma to the following two subgraphs of gn plus 1. And what we find is that for both these subgraphs, with j equals 6 alpha n, we must pebble 250 alpha n of our entry nodes in order to pebble these 7 alpha n exit nodes. And since there's 250 alpha n entry nodes on each of these graphs, and 500 alpha n is more than 34 alpha n plus 1, we have found a time interval that satisfies the conditions of our inductive hypothesis. Then for case 2, we do something very similar to what we did for case 1. We are now pebbling 7 alpha n of these nodes instead of the previous ones, but we still have a time interval where there's 3 alpha n pebbles. So we can extend backwards the same way as before, look at some slightly longer subgraphs, which are still super concentrators, but we apply the same lemma, we get the same thing, that there's 500 alpha n is greater than 34 alpha n plus 1 entry nodes that are being pebbled during this time interval, and there's 3 alpha n pebbles for the entire time interval. Case 3, again, is very much similar to the first two cases, where we pebble 14 alpha n of these exit nodes here. And by the pigeonhole principle, that means for one of these, we're going to pebble at least 7 alpha n of the exit nodes. So we can assume without loss of generality that it's the top one. And then we can again extend backwards the same way we did before, and we can apply our lemma to this super concentrator and this super concentrator to get the same result as we did for the first two cases. Finally, we can look at our non-special case. So if none of those three previous cases hold, what can we say about our graph? Well, first of all, at the end, we're trying to pebble 28 alpha n pebbles. And now we can look at the time interval in which we pebbled the first 14 alpha n of those. And since we're not in case 3, we know that there must be some time t0 at which there's less than 3 alpha n pebbles on the graph. But that means in the interval t0 to t, we start with less than 3 alpha n pebbles. And since we pebbled at most 14 alpha n pebbles so far, we still have 14 alpha n pebble nodes left to pebble. Then by the pigeonhole principle, one of these has 7 alpha n nodes left of Pebble, so we'll say it's this one. Then we can apply our lemma to this graph, and what we find is that there are 256 minus 3, so 253 alpha n nodes in this section that get pebbled during this time interval. And then since we start with at most 3 alpha n pebbles on the graph, and we are pebbling at most 253 of these nodes, we can apply our inductive assumption to this graph to see that there must be some time interval t1, t2, t1, t2, such that during this time interval, there are alpha n nodes on this graph, and we pebble at least 34 alpha n of the pebbles on this graph. Then, since we're not in case 2, during the time at which we pebble the first 7 alpha n of these, we know that there must be some time t3 at which there are less than 3 alpha n pebbles on the graph. So from the interval t3 to t2, we start with less than 3 alpha n pebbles on the graph. We have to pebble the remaining 27 alpha n pebbles on this graph, or on this section, which means we need to pebble at least 24 alpha n pebbles on this section, which means we can apply the inductive assumption to this graph gn1 to find the same thing, that there's some interval within this t4, t5, t4, t5, where the entire time there's alpha n pebbles on this graph, and we pebble 34 alpha n of these. Then, since we're not in case 1, we can again say when we pebble the first 7 of these, there's a time t6 where there's less than 3 alpha n pebbles on the graph. So during t6, t5, we start with less than 3 alpha n pebbles. We need to pebble at least 27 alpha n of the remaining of these. And then we can finally just apply our lemma to this graph to see that this means we need to pebble 253 alpha n of the entry nodes here. And clearly 253 alpha n is more than the 34 alpha n plus 1 pebbles that we wanted to pebble as an entry node. And from this and this, we know that there are at least alpha n plus 1 pebbles on the graph the entire time. So we finally proved what we wanted for the most general inductive case. So with that, we can finally say that for a graph Gn, we know that for each graph, we can find a sinc vertex that requires at least 2 to the n over 2 to the 8 pebbles to pebble, and therefore that it takes theta of v over log v pebbles to win the pebble game on this. So we can't improve what we showed in class. So maybe next time we should just stick to skipping pebbles.